Hi, this is Daniela, and this is my Lab 5, Faraday's Law. So here's a little introduction of our lab. So the purpose of the lab is to understand Faraday's Law by collecting time data of a magnet falling through an aluminum tube. So some of the concepts that we're going to go through in this lab are Faraday's Law, Biot-Savart Law, Newton's second law, and Newton's third law. So here are some of our key equations that we're going to be using throughout this lab. So the equation on the left is Faraday's law, the middle equation is Biot-Savart law, and the last equation is Newton's law. So a quick little summary of our results. So our experimental data, we got 1.12 seconds, and in our computational model, we got 1.476 seconds, and this is the time that it takes the magnets to fall through the tube. So with this being said, the system would be the magnet and the surroundings would be the tube. So here are our measurements of the tube. So the length was 0.3 meters, the width was 0.005 meters, the inner radius was 0.015 meters, the radius was 0.03 meters, the mass of the magnet was 0.025 kilograms, the mu magnet is 2.2, which is what we got in our lab 3, and the average time was 1.12 seconds. So in this lab, we did 5 trials of dropping the magnet through the aluminum tube. And so we got our average to be 1.12 seconds. So with our glow script, this is the computational model. In step 1, this was inputting all of the geometry of the tube, which was the givens that we got from the measurements, was what we calculated when we were measuring the tube, the radius, the mass of the magnet, etc. And in the second step, we define the magnetic field of the dipole in any point of the tube by using the B field law, the Biot-Savart law. And in the bottom right corner is going to be the equation that we saw in our third slide. And this is how we calculated the magnetic field of the dipole. Then I calculated the flux by first calculating the time derivative of the flux using Faraday's law that we talked about. Then I found the current in a single ring of the tube by using the equation I is equal to the derivative of flux over resistance. So what we did was that we got the derivative of the flux and we divided it over the resistance. Then I calculated the force of the loop and the force of gravity as well as the net force. Then I applied the momentum principle as the magnet was falling through the loop. So this was the output that we got from the glow script. As you see here, we got that it ended at 1.476 seconds, which was the time that the magnet reached the bottom when it was dropped through the tube. This did differ from our experimental data, which was 1.12 seconds, and this could just be human error of dropping the magnet, making sure that no force was applied. Maybe there's a force that was applied, which caused it to take less time for it to go through the tube. So our discussion questions. What if the resistance of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So due to Ohm's law, the induced current would be very large, and this would make the time it takes to fall through the tube even larger. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? So this would be in reduced induced current and reduced magnetic field, causing the time it takes the bar magnet to fall through the tube to decrease. And the model would have less rings in our computational model. Thank you.